In this video we shall learn how Gibbs-Donnan equilibrium applies in case of living tissues or a cell. In one of the previous videos, we saw how presence of impermeable anion on one side of a semipermeable membrane leads to slight excess of potassium ions on that side. This is followed by outward diffusion of the same along its chemical potential. However, exposed negative charge, on the side of impermeable anion, serves as electrical potential, and prevents further back diffusion of potassium ions. Essentially, very few K+ ions will have moved from side B to side A, before it is further prevented. Thus, electrical and chemical potentials will become equal and opposite at equilibrium, and the side having impermeable anion will continue to have a slight excess of cations. Now, let us borrow this hypothetical analogy to a living cell. Our cell membrane is selectively permeable, having selective protein channels for movement of ions across it. In the resting state, cell membrane is more permeable to potassium ions than to sodium ions. Similarly, permeability of different ions across the membrane depends on the presence of their selective protein channels. The distribution of ions in the ICF and ECF, as shown in this figure, is the end result of their differing permeabilities across the cell membrane along with the electrical potentials exerted by the ions, on either side, upon one another. Now, let us take another factor into consideration when Gibbs-Donnan equilibrium is considered. The process of osmosis is invariably associated during movement of ions. In the previous hypothetical analogy, side B will have a higher number of osmotically active particles at equilibrium that leads to a higher osmotic pressure. As shown, this causes osmosis of water into side B and resultant expansion of its volume. If we want to prevent this from happening, we need to pump water out of side B into side A. Such a pump will continuously operate and prevent water excess and the resultant volume expansion on side B. Hence, it will hold the membrane in its place despite of side B's higher osmolarity. This is what happens in case of a cell. It has a slightly higher osmolarity compared to ECF due to Gibbs-Donnan equilibrium. So osmosis of water can cause cellular swelling that needs to be prevented by pumping water out. How can we devise such a water pump for a cell? Osmosis in biological tissues is associated with osmotic pressure or number of osmotically active ions. In case of body fluids, the major determinants are the sodium, potassium and chloride ions. So, to achieve our goal, we have to decrease the number of osmotically active particles on side B, or the intracellular side. Now, this can be done by an active ion pump like the ubiquitous sodium-potassium pump. The pump moves out 3 sodium ions out of the cell against 2 potassium ions inside of the cell, both against their respective concentration gradients. Hence, it leads to loss of a cation from the cell. The pump uses ATP and tries to prevent excess buildup of cations on the intracellular side, thereby decreasing osmotic pressure and water osmosis. So, to summarize, we have a Gibbs-Donnan equilibrium working in the first place to build up an excess of cations on intracellular side having an impermeable anion. But, this can lead to osmosis and enlargement of volume of side B. So, we also have the second mechanism already in place, that is, the ubiquitous sodium-potassium pump in the membrane to continuously pump out ions from side B to side A, that is, intracellular side to extracellular side. This will ensure that water does not accumulate and the cell does not enlarge. These two opposing processes occur in a dynamic and instantaneous manner continuously to maintain a balance across cell membrane. Therefore, the first application of Gibbs-Donnan equilibrium is about control of cell volume across cell membrane. Now, about the second application. As we all know, the inside of the cell membrane is relatively electronegative compared to the outer side. This is known as the resting membrane potential. The equilibrium maintains a slight excess of potassium ion within the intracellular fluid due to the presence of impermeable negatively charged proteins. Back diffusion of these potassium ions into ECF exposes the negative charge on the proteins, which is manifested as the negative resting membrane potential. Another application of this process is about generation of plasma oncotic pressure in the intravascular compartment by plasma proteins, chiefly albumin. Albumin is the most abundant plasma protein, and has a negative charge on it. Also, it is impermeable across the capillary endothelium. The interstitial fluid is deficient in plasma proteins normally, but has a similar ionic composition with that of plasma. Presence of an impermeable anion on one side of capillary endothelium leads to operation of Gibbs-Donnan process, and, at equilibrium, a slightly higher sodium ions are present in the intravascular space compared to the interstitial fluid. Excess sodium ions in plasma causes osmosis of water into the intravascular compartment. So, in essence, the oncotic pressure exerted by albumin in the intravascular space is due to the presence of slightly higher sodium ions in plasma attached with albumin. The oppositely directed oncotic pressure and capillary hydrostatic pressure, across the selectively permeable capillary endothelium, balances the Starling forces in microcirculation. This prevents excess outflow of water in the interstitial space and hence edema formation. See you in the next video on Nernst equilibrium potential. Thank you for watching.